Hello and welcome everyone to this first podcast on the chemical basis of life. In this podcast, we're going to focus on a few fundamental features of chemistry that are essential to begin our discussion of life, in particular cellular life. We're going to begin by talking about matter, and then we'll talk about the atomic structure, and then we'll talk about molecular bonds. But let's go ahead and get started with matter. So let's begin with a simple definition for matter. In general, we can think of matter as anything that takes up space and has mass. As some examples of some living and non-living matter, let's look at this picture of my son Jackson sitting on a lawn of a fairly famous person. I'll let you try to guess whose lawn that might be. But anyhow, let's think about living matter as we see in this picture here. So anything that takes up space and has mass. So certainly the person here in the middle, Jackson. There's some other people in the background here as well. So let's put people. They are matter. But we also have like the grass. There's a pigeon way back there. We can't see them, but certainly there are soil microbes and other organisms living in the soil that we can't see. There's also non-living matter. This would certainly include, say, the clothes and shoes that people are wearing. It would also include this cement column and the gate in the background there. And there's a car way back there. These are all matter. Now we're going to focus primarily with living matter, this being a cell biology course, but all matter is made up of atoms. The tiny structures that you learned about in chemistry and we're going to develop here in cell biology are responsible for everything we see in this picture. Okay, so let's go ahead and spend some time talking about atoms. To begin this discussion, let's look at this periodic table. This periodic table has 118 elements. These different elements can combine with elements of the same kind or with different elements to make matter. So they combine to make matter. So what is an element? Well, elements consist of atoms, each with a characteristic number of protons. And we'll talk about protons in just a moment. But if you change the number of protons, the element changes. So any given element that is composed of a bunch of these atoms, but those atoms have to have the same number of protons. So let's think about the structure of an atom. At the center of an atom is the nucleus. The nucleus contains the protons and the neutrons. Outside of the nucleus are the electrons. Only a very small part of the atom is the nucleus. Your book makes a nice comparison. It says if you're looking at a large football stadium, and if that were representative of an atom, the nucleus would just be a single pea in the middle of the football field. So it's a very small component of it. And these electrons, as we'll talk about later and you'll talk about in chemistry classes, will move around the outside of the nucleus, leaving large amounts of space here within the atom itself. So let's go ahead and look at one of my favorite elements. We all have our favorite elements, and this is one of mine, krypton. And it's abbreviated Kr. And if you look over here on our periodic table, we see a number here, 36, and then we see this number here at the bottom, which is 84. This number on top is the atomic number. This number on the bottom is the mass number. The atomic number represents the number of protons. The mass number is the number of protons plus the number of neutrons. I should warn you that In some textbooks, in some periodic tables that I've seen, in fact I think your textbook does this, they will reverse these numbers. The mass number will be on the top and the atomic number will be on the bottom. It shouldn't matter as you're interpreting them, because the atomic number will always be less than the mass number, because the atomic number is just the protons and the mass number is the protons and the neutrons. So it does get a little confusing, but just remember atomic number is less than the mass number. So by looking at the atomic number and the mass number, we should be able to calculate the number of protons, the number of neutrons, and the number of electrons. The number of protons will always be the atomic number. So in this case, the number of protons in krypton is 36. The number of neutrons will be the mass number, 84, minus the atomic number, 36, which equals 48. So there are 48 neutrons in an atom of krypton. The number of electrons in a neutral atom will always be the number of protons. So the number of electrons is, in this case, 36. Remember what I said earlier. The number of protons is characteristic of this atom. If you change the number of protons, and you can do that, but when you do that, it is no longer krypton. So if you change the number of protons to 35, krypton becomes bromine. Now the number of neutrons here, I indicated here as 48. In reality, this number is just an average. There's a range between, say, 46 and 49 neutrons. It's close to 48, but this is just an average. These different, I'm going to remove this here periodic table just to give us some more room. Now each atom of krypton that has a different number of neutrons, 45, 46, 47, 48, 49, these are all called different isotopes of krypton. They're still krypton, they just have a different number of neutrons. So here let's write different number of neutrons. Now as I mentioned, you can also change the number of electrons. And when we change the number of electrons to say 35 or 37, you change the overall charge of the atom. Instead of being neutral, as I've written it here, it becomes positively or negatively charged. These positively or negatively charged forms of the atom, say the atom of krypton, these are called ions, charged ions. In any given problem that I ask on a test or a quiz, where I ask you to identify the number of protons, neutrons, or electrons, unless stated otherwise, you can assume that it's a neutral atom, where the number of electrons will equal the number of protons. Okay, now let's look at the structure and organization of protons, neutrons, and electrons within an atom. So let's begin by looking at carbon. Carbon is abbreviated as just a capital C. And remember that within the nucleus of the atom carbon will be the protons and neutrons. The mass number for carbon is 12, and the atomic number is 6. Because of that, we know we have 6 protons because of the atomic number, and we know we have 6 neutrons. 12 minus 6 gives us 6. Okay, now let's consider the electrons. And we know the electrons in an uncharged carbon will equal the number of protons. So we should have 6 electrons. Now the electrons are not just randomly thrown around the outside of it. There's a precise order. You may remember from chemistry that electrons move around this nucleus in orbitals. Each orbital contains 2 electrons. So for instance, in carbon, we will have 2 electrons like this for this one orbital, and they will move around the atom. Now we need 4 more electrons. These other 4 electrons are located in the next electron shell. There is never more than 1 orbital or 2 electrons in this first shell, the inner shell. So here we have the second shell. It so happens that these electrons for carbon are unpaired in this outer shell. So we have these 4 orbitals, but they each only have 1 electron. This outer shell, whether we're talking about 1, 2, 3, or 4, but in this case, carbon, we're talking about the second shell, is referred to as the valence shell. The valence shell is the outer electron shell of an atom, and we call these electrons valence electrons. These are the ones that are going to be involved in chemical reactions. We'll see in a moment that we have 4 of these electrons, all of them unpaired, so they can be involved in 4 separate chemical reactions. They can bind to 4 other atoms. Another term to throw out at you is the valence number of an atom. The valence number is the number of unpaired electrons. So we say that carbon's valence is 4. Oxygen, for example, has 2 unpaired electrons, so it has a valence of 2. If you would, look at figure 2.3. There are several elements here. I would like you to focus on hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. The reason I want you to focus on these is that these are the most abundant elements within a living organism. I'm not going to make you memorize the number of electrons in each one of them, but you should be able to look at the atoms in figure 2.3 and identify which is the valence shell, what are the valence electrons, what's that element's valence, and also identify which one of these is going to be involved in chemical reactions. Again, you don't need to memorize that table, but if I show you a part of it, you should be able to interpret it. Okay, next I'd like to talk about chemical bonds and how they form compounds and molecules. So before we start talking about bonds, let's talk about the difference between a molecule and a compound. Molecules are 2 or more atoms that are chemically joined. A compound is a molecule with 2 or more different atoms. For instance, the following are molecules: oxygen, CO2, that is carbon dioxide, ATP, I won't draw the structure, but it contains many different atoms, and water. These are all molecules because they contain 2 or more atoms. So of these molecules, carbon dioxide, ATP, and water are also compounds because they are composed of different atoms. They're still molecules, but they're a special kind of molecule that we call a compound because it contains 2 or more different atoms. Oxygen is a molecule. It's not a compound, it's only a molecule. Now that we know the difference between a molecule and a compound, let's talk about the chemical bonds that help form them. I want you to know these 4 different bonds. You should know what a covalent bond is, you should know what an ionic bond is, and you should know what a hydrogen bond is. And we'll spend more time talking about hydrogen bonds in the next podcast. And then you should know what van der Waals bonds are, my favorite bonds. But let's begin with covalent bonds. Covalent bonds are strong bonds. In fact, of these 4, they are the strongest. So these are strong bonds that form when electrons, E with a minus sign is an abbreviation for electrons. So when electrons are shared between 2 atoms. They can be 2 of the same atoms, they could be 2 different types of atoms, but the key is that the electrons are shared. For instance, if we had 2 hydrogens, hydrogens have 1 electron in the outer shell, it's a valence of 1. These electrons are shared with each other to form this covalent bond where these 2 hydrogen atoms share the electron. The next one I'm going to talk about are ionic bonds. Ionic bonds are less strong compared to covalent bonds, but they are stronger than hydrogen or van der Waals bonds. So they're less strong bonds that form when electrons are transferred between 2 atoms. The key is that these electrons are transferred. So for instance, as an example of an ionic bond, let's talk about our favorite ionic bond of sodium chloride. And to do that, let's talk about sodium here. Sodium contains 11 electrons in its uncharged form. Chloride contains 17 electrons. As this ionic bond forms, sodium loses an electron. And this results in a sodium atom with 10 electrons. It is less negatively charged now. And as a result of being less negatively charged, because it lost this negative electron, sodium is now positively charged. It's a positively charged ion. Chloride in this interaction will gain an electron. Will gain this electron. And now chloride will have 18 electrons. And as a result, it is more electronegative and will be negatively charged. So now that sodium has transferred an electron to chloride, it allows these two atoms to come together and form this ionic bond. Again, it's not as strong as a covalent bond, but it's still pretty strong. And it's the result of one atom transferring an electron to another atom. I'm going to erase this bottom part here so we can talk about van der Waals. I'm going to come back to hydrogen because I just need a little bit more space to describe hydrogen bonds. But let's skip ahead to van der Waals. Van der Waals of these four are the weakest. So these are weak interactions that form due to electrical attractions between two molecules. These charges are transient. And the best way I think to describe them is to think about a given electron or a given atom that has these, I'm just going to put A here for atom, that has these electrons moving around the outer surface here. At any given time, these electrons could accumulate on one side of the atom, leaving this side more negatively charged. This other atom may, at any given point, have more electrons on this side and none over here. So for a very brief moment, this atom has more negative charges on this side, this has fewer, and because of that, they will form a very weak association with each other. Now, individually, van der Waals interactions are, as I said, very weak. However, together, when you get a lot of van der Waals coming together, it will form a very strong interaction. Probably a good classic example here is if you think about the gecko lizard. Gecko lizards can climb up smooth surfaces like glass and other smooth walls. And the way they're able to move up glass or walls is because of these very weak interactions between their feet and the surface, these van der Waals interactions. So again, van der Waals are transient. Singularly, they're very weak, but together they are very strong. Now, I'm going to erase this so I can spend a little bit more time talking about hydrogen bonds. Alright, so hydrogen bonds. These are weaker individually than covalent and ionic bonds, but stronger than van der Waals. Just like van der Waals, though, even though they're weak singularly, when you have a lot of them together, they are very strong. So, a hydrogen bond is a bond that forms between two polar groups, and they form due to an electronegative attraction. Hydrogen bonds will form between a hydrogen atom and various electronegative atoms, such as nitrogen, oxygen, fluorine, as well as other electronegative atoms. So as an example, hydrogen, which has a partially positive charge, will form a hydrogen bond with one of several electronegative atoms. For instance, it may form a bond with nitrogen, which has a partially negative charge. We're going to talk about this in great detail in the next podcast when we talk about the special properties of water, because hydrogen bonding within water molecules is critical for life. So we'll spend quite a bit more time talking about hydrogen bonds, and we'll come back to this bond, hydrogen bonds, and the other bonds throughout the semester as we move forward with the complexities that we'll find within the cell. Well, that ends this podcast, and I'd like to close with a quick summary. In this podcast, we began by talking about matter and we talked about how matter was made up of atoms. The complexity of all the matter we see is made up of these tiny little atoms. And then we moved into talking about atomic structures. In this discussion, we talked about the number of electrons, protons, and neutrons, and how you can determine those by knowing the mass number and the atomic number. We also introduced terms such as ions and isotopes. We talked about the difference between a molecule versus a compound. And then we just closed with talking about 4 different bonds and how those bonds are important in forming molecules and compounds. And in order of strength, we talked about covalent bonds, ionic bonds, hydrogen, and van der Waals. Okay, that ends this first podcast. If you have any questions at all, please make sure you come see me.